Can people see my screen and hopefully hear me? All right. So let's go ahead and get started. Thanks, everyone. Thank you all for joining us for our third Paleoclimate Advances Webinar Series, or PAWS for short. I'm Clay Tabor. I'll help out with hosting today. Before we get into the talks, I just have a few reminders about our values and our format. So the goals of PAWS is to provide a welcoming space for the exchange of ideas on paleoclimate advances. So please make sure to be respectful and supportive of each other, especially during the question and answer and the discussion. Also, please remember to consider nominating people for future speakers. Remember, we strongly encourage self-nominations as well. So our format's the same as in the past two times. We'll start out with 20 minutes for talks. I'll let the speakers know when we have 2 minutes remaining. And after each talk, there'll be about 5 minutes for question and answer. So please save your questions for the end of the talks and raise your hand at that time or post them in the chat. And after we've had both talks completed with those 5 minutes for question and answers, then we'll have an additional 10 minutes for more general discussion. And these talks are being recorded and will be posted online as well. All right, so we have two exciting talks today on paleoclimate and climate sensitivity. Our first speaker is Dan Lunt. Dan is a professor of climate science at the University of Bristol. His research centers on past climate change with a focus on understanding how and why climate has changed in the past and what we can learn about future from the past. He's a lead author on the IPCC 6th Assessment Report, and he leads the International DeepMIP program. He was also founding and chief executive editor of the Journal of Geoscientific Model Development and is an affiliate scientist at NCAR. Our second speaker is Martin Renoult. Martin is a PhD candidate currently at Stockholm University. He studies paleoclimate modeling and reconstructions and what we can learn about climate dynamics from paleoclimates. His work has been on understanding climate sensitivity and feedbacks on many different time periods, from the last glacial maximum to the Pliocene and even snowball Earth. He holds a BS from the University of Angers and a master's from the University of Bordeaux. So with that, and to make sure we have plenty of time for the talks, I'll go ahead and stop sharing and let Dan go ahead and present on paleoclimate sensitivity and the IPCC. All right, so you can go ahead.
Great, thanks very much, Clay, for the intro. I'll just share my screen. Hopefully you guys can see those slides now. Yeah, so I'm going to really, well, first of all, I'm very briefly going to just introduce the chapter 7, which was the chapter I was involved in the most recent IPCC report. And then for most of the talk, I'll focus on climate sensitivity, and in particular, the paleoclimate sensitivity assessment that we carried out as part of AR6. So, but just to kick off as a very brief intro, this is our chapter 7, the Earth's energy budget, climate feedbacks and climate sensitivity. So just to give a bit more of a broad overview of the whole chapter and the things that are covered in there, I think these new elements that it talks about down here is quite useful. So basically a large part of the chapter was looking at trying to sort of close the energy budget, really looking at the amount of energy coming in at the top of the atmosphere and going out, and how that's changed in the historical period, and how that corresponds to changes in energy reservoirs, like in particular total global ocean heat content. There was work done or assessments done on sort of the concept of radiative forcing, really, and making sure that we include things like radiative adjustments in there. And there was a lot of work on assessing new understanding of cloud feedbacks and the sort of net effect of all clouds, both you know, spatially and different heights and what have you, to assess an overall cloud feedback. A lot of work on the pattern effect and how we understand recent historical changes in terms of patterns of sea surface temperature change. And then the bit that I'm going to focus on is this new assessment of climate sensitivity. But then finally, there was a section also looking at sort of quantifying some of these key metrics that are used by policymakers to link emissions of CO2 and methane to temperature targets. So that's sort of an overview of the chapter. Like I said, I'm going to focus myself on climate sensitivity in the 6th assessment report. And in particular, I guess the first thing to say is even the definition of climate sensitivity changed a little bit in this report, in that we think about the global mean annual mean temperature, equilibrium temperature response to a doubling of atmospheric CO2. But a new thing in this report was that we made it very, very clear that this was actually including all feedbacks in the climate system, apart from those associated with ice sheets and those associated with CO2 itself. So in previous reports, it was more done on sort of the time scale of the feedbacks, but this time it was a more sort of physically based definition. Just very briefly, I'm sure all of you know this, but climate sensitivity, ECS, is a key metric because it allows us to make a link basically between CO2 concentrations and temperature. So for example, if you have a key temperature target like 1.5 degrees warming, it basically tells you what equilibrium CO2 concentration is consistent with that. Similarly, if you think you're going to stabilize your CO2 concentrations at a particular level, it will tell you what the equilibrium warming will be. And yeah, it's a key metric across science, and it's also an input to many climate impacts and integrated assessment models. So before AR6, this was the situation how ECS, climate sensitivity, how different key assessments, mainly from the IPCC here, from the 1st assessment report to the 5th assessment report, how that assessment had changed. And you can see the key thing, as everyone knows, is that really the overall assessment of the likely range of climate sensitivity had not really changed since the mid-70s, since the first Charney report. So it was really interesting starting work on this chapter to think, well, can we go beyond that? Are we going to be able to tighten these constraints or not? Maybe they're even going to widen, like they did between AR4 and AR5. With because improved understanding doesn't always lead to narrower estimates. It can actually, if you improved understanding, can mean actually your uncertainty gets larger. So this time around, we had 4 lines of evidence to base our assessment on: process-based estimates, and I'll go through these briefly. Process-based estimate, the historical record, paleoclimates, and emergent constraints. So first of all, the first of these process-based assessment of climate sensitivity, this is basically trying to assess the magnitude of all the feedbacks that you can think of in the climate system, and then basically adding them together, defining them with a feedback parameter with units of watts per meter squared per Kelvin, and then basically adding them all together to get an overall feedback parameter. So key, things like surface albedo feedback. But like I said at the beginning, a lot of new work on cloud feedbacks over the last 4 or 5 years meant that was a lot of the chapter actually was looking at new assessments of cloud feedbacks in different regimes, and in particular changes in confidence of the low cloud amount feedback and cloud phase change feedbacks. And some of the input to this was the CMIP6 models themselves, which can be used to estimate some of the sort of basic feedbacks, like the Planck feedback, water vapor and lapse rate feedback, surface albedo. Like I said, here we've got the large uncertainty in the cloud feedbacks. But also this time round in AR6, there was quite a bit more work on looking at some of the more sort of system-y type feedbacks, like the biogeophysical and non-CO2 biogeochemical feedbacks. And so, for example, assessments being made of feedbacks associated with, for example, sea salt, DMS, dust, ozone, etc., all assessed through various different lines of evidence. In terms of the biophysical feedback, this was an element, this was a part where paleoclimate played a role. So in particular here, what we're talking about really is the albedo feedback associated with vegetation changes in response to temperature change. And there are a few modeling studies that have looked at this, where, for example, people have run models into the future with and without vegetation feedbacks. But in terms of observational lines of evidence, because it's quite a long timescale feedback, then the paleoclimate can provide some data for this. And in this case, we use the Pliocene, the mid-Pliocene 3 million years ago, as a line of evidence here, because there's pollen data that tells us something about how vegetation types were different in the Pliocene when CO2 was high, temperature was high. And we were able to make a sort of first order estimate of the feedback parameter associated with that vegetation feedback from paleo observations. And it turned out that it was actually quite a bit larger in magnitude than the estimates that we get from many models. So that was the first example I have really of paleoclimate coming into the overall assessment of climate sensitivity through characterizing the size of vegetation feedbacks. But also another part of this chapter was looking at the non-linearity of some of these feedbacks and how they vary themselves as a function of temperature, because that can be important for assessing, for example, if you do climate model experiments where you quadruple CO2 rather than doubling CO2, how much, the normal assumption is that the feedback, you're basically going to get double the temperature change from a quadrupling than you do for a doubling. But if the feedback's very non-linearly, then maybe that's a poor assumption. And this is something where paleoclimate can have something to say about this. If you can estimate temperature and CO2 changes across a range of different states, like we did like people have done, looking at, for example, the early Eocene compared to the late Eocene compared to the Pliocene, or looking at feedbacks at the LGM compared to the present day, then you can get a feeling for the magnitude of this non-linearity. And there's again a few modeling studies that have done this, either under modern or paleo conditions, and observational studies, again from pure paleo data. And we put all these together on this graph, which shows the feedback parameter strength on the y-axis. So you basically got increasing climate sensitivity as you go up here as a function of background temperature. You can see these are sort of quaternary records looking at climate sensitivity in the LGM compared to the modern, and then you've got some other paleo records looking at, for example, I think this is the early Eocene compared to the late Eocene compared to the early Eocene, or something like that. And you see that in general, there is, the majority of the lines of evidence indicate an increase in sensitivity as we go to warmer climates, but there are a few records that show the opposite, and there's a lot of scatter in terms of both the magnitude of the overall climate sensitivity and the gradient in these lines, so how sort of the strength of that nonlinearity. So obviously still a lot of work that could be done purely from the paleo data side here. The second line of evidence was looking at the instrumental record, the last 150 years or so. If you know what the various different forcings are that have caused that temperature change, you've got an estimate of the temperature change itself, then you can estimate the climate sensitivity. If you take into account some of the, and this is, again, something sort of new in this report compared to the previous report, if you take into account the fact that some of the sort of the lags, the time scale of response of the climate system and how feedbacks change as the patterns of sea surface temperature change are evolving in response to the CO2 forcing. So the bit that I really want to focus on, though, is the third line of evidence, which is using paleoclimate data to constrain climate sensitivity. So just as a very quick example, if you take the last glacial maximum, for example, we have very good estimates of what CO2 concentration was at the time. We've got paleo data that tells us something about the temperature response at the time that you can convert to a global mean temperature, with a given uncertainty associated with the uncertainty in the calibration of the proxies and the uncertainty in going from individual records to a global mean. As long as you take into account all those uncertainties and take into account the forcing effect of the ice sheets, which is not itself included in the climate sensitivity, if you sort of take that out of the forcing and the response, then it allows you to estimate the climate sensitivity. And basically, to assess the climate sensitivity from these various different lines of evidence, we basically accumulated all the studies that we have had since AR5 and sort of tabulated them along with their estimate of ECS and their uncertainty. You know, there are several pages in the report outlining the details of this assessment, but just very much in summary, we went for a sort of quite a qualitative approach, really, taking into account, looking at these different studies to come up with a, you know, eventually we had to come up with a quantitative estimate, but our approach, our methodology was to really look at the sort of qualitative lines of evidence and to come up with the overall assessment. So, for example, none of the studies that we looked at, none of the studies that have been published since AR5 had a lower estimate, sort of even at their lower range estimate of ECS. None of them had a, well, the lowest was 1.6 degrees for a CO2 doubling. So we said it was very likely that ECS was greater than 1.5 purely from the paleoclimate evidence. We were asked also to come up with a best estimate, and again, there are lots of different ways of doing this, sort of to get a central estimate. But you know, we did several different methods, and they all came up with a similar answer. So, for example, if you just very simply take an average of the the first thing we decided to do is actually take out those studies that came from the transient records of the Quaternary, because you've got lots of complications associated with how much of the response is associated with ice sheets, how much of it is associated with direct orbital forcing, and also, basically mainly due to the complications of the orbital signal that's in there. If you take those ones out and then you average separately over all the LGM studies and the pre-Quaternary studies, then basically you get an estimate of something like just over 3 degrees C. So our best estimate was somewhere between 3.3 and 3.4. Again, if you didn't look at the pre-Quaternary, if you took out the pre-Quaternary studies, then if you look at the upper range now of previous work, the LGM, the highest value was 4.4. If you look at the pre-Quaternary, the highest was 4.9. But take into account the state dependence, the fact that we think climate sensitivity increases with increasing temperature, we said it was likely that ECS was less than 4.5. Just a reminder, the language, the sort of very likely is a 90% confidence. The likely is a two-thirds confidence. And then also we looked at, again, if you exclude those pre-Quaternary studies, the evidence that it was extremely unlikely, which I think is the 95% confidence that the ECS was below 8 degrees. So that was our overall assessment from the paleo data, that third line of evidence. In terms of the fourth line of evidence, that was from emergent constraints, but I'm not even going to mention these at all, because I'm sure Martin will give us a very good, nice introduction to those. So we have these 4 lines of evidence anyway, in terms of, here's the ECS on the x-axis here, the 4 different lines of evidence with their central estimate, their best estimate or mean value, their likely range, and their very likely range, and then for some, the sort of extremely likely range. And to come up, and we combine these 4 lines of evidence to come up with an overall combined assessment. How did we do this? Again, there are different ways this could be done. You could go down a sort of quantitative approach, using sort of Bayesian analysis like they did in the Sherwood report. But basically that work was really just emerging when we started this work, well, even when we were in the middle of this work. And we decided again to go down a more sort of qualitative approach. And in the report, it sort of outlines that quite nicely, I think. And it says that, you know, basically as a general principle, if you have several different independent lines of evidence that all have a certain range of ECS, then if you combine those sort of in a Bayesian sense, then your overall uncertainty is going to be less. And that was the sort of principle that we used when constructing the overall combined assessment. And if you look at that compared with what has happened over the previous reports, then you can see that with these, you know, considering these different lines of evidence independently, then we ended up with a sort of a more tightly constrained overall assessment of ECS than has been the case in previous reports. So sort of a likely range of 2.5 to 4 with a very likely range of 2 to 5, best estimate of 3. Just to finish off, what are the implications of this? Well, one of them is that if you look at future projections in the report, this is the projections going out to 2100 relative to sort of more the more recent in terms of global mean temperature response under different SSP scenarios. And this is an estimate where you've basically taken the average of all the CMIP6 models together. But in this case, you've only taken those models where that have a climate sensitivity and an intrinsic ECS themselves that was within the very likely range that we assessed, that range of 2 to 5 degrees. And you can see that it has the effect of actually bringing down, decreasing the temperature estimates from the models. And the reason for that is basically some of the very high climate sensitivity, basically because you exclude more high climate sensitivity models than you exclude low climate sensitivity models by doing this, and you end up with an overall decrease in temperature. And what I always say is basically because the paleoclimate data was one of the lines of evidence that we used in that assessment, then basically the paleoclimate data has effectively brought down these projections of the future in the IPCC report.
About 2 minutes.
Sorry, Clay?
Oh, about 2 minutes, sorry. Okay,
great. Well, this is my last slide. Just again to show sort of some of the implications of this from the paleo side. Again, this is one of the other none of the figures in the report. And what we're showing now is 5 different time periods. We've got the historical record, so like roughly 1850 to the recent. We've got sort of 1970s to today here. We've got the last glacial maximum, mid-Pliocene warm period, the early Eocene. And for all of these, we've got the global mean temperature relative to pre-industrial, basically. So, for example, this shows that, and in the black squares, we've got the black circles and their uncertainty. We basically got the observations. In this case, this is sort of historical observations of warming since 1850. Here we've got about 1 degrees C or so. Warming since 1975, about 0.5 of a degree in observations. Eco-warming, for example, about 15 degrees compared to pre-industrial. What the circles are showing you are GCM estimates of that same observed warming. So each circle is a different GCM. These are all CMIP6 models for the historical and post-1975. Once you get out to the eco, none of these are, well, actually, one of these is a CMIP, 2 of these are CMIP6 models, but fewer and fewer CMIP6 models once you get to the paleo simulations. Those that are red and blue are basically GCMs or ESMs that have a climate sensitivity that is outside the range of our assessed climate sensitivity. So the red ones have an ECS greater than 5, and the blue ones have an ECS less than 2. And what it shows, I think, very nicely is basically you can almost create a model with any climate sensitivity, and it can still do a very good job of warming since 1870. It can reproduce the recent warming very well on those timescales. Even if you look at the warming since post-1975, you can construct a model that has a climate sensitivity of less than 2 that still fits the observations very, very well. Whereas once you get to the paleo and you've got an equilibrium warming state, it is much harder to construct a model with very high or very low climate sensitivity that fits the data. And so again, it's a sort of another independent line of evidence that indicates that our assessment of climate sensitivity was probably fairly realistic. Or you can look at it and say that the paleoclimate is a very good, the observations of paleoclimate is perhaps a very important thing to do as part of your model development process, because if you do that, it will perhaps indicate if your model is either too sensitive or not sensitive enough. So I'll leave it there, and thanks very much.
Great. Thanks, Dan, for a nice talk. Are there a few quick questions for Dan? So feel free to raise your hand or put them in the chat. Oh, Ran, go ahead.
Thanks, Dan, for the very interesting talk. I just had a question here. So when you talk about for example, this last slide, when you talk about the equilibrium climate sensitivity, does the estimate include the vegetation feedback?
Bear with me. So in the observation, so if you take, for example, well, let's take the eco for the paleo estimate, the proxy estimate themselves, this black circle here, does take into account vegetation feedbacks because it's observations of the actual temperature change, and the real world had vegetation feedbacks, and so this estimate of global mean temperature change does include those feedbacks. These GCM simulations actually also include that vegetation feedback, because part of this experimental design was prescribing vegetation change in accordance with primarily pollen records from the Eocene. So although the GCMs didn't include vegetation feedbacks themselves, because they had prescribed vegetation in them, they did effectively include the effect of those feedbacks. Same with the Pliocene. The model experimental design includes changes in vegetation. So again, those feedbacks are included in the observations and in the response. When it comes to the LGM, again, the paleo observations themselves include those feedbacks, but my understanding is that most of these GCMs had fixed vegetation, although I'm not sure about that. Some of them, one or two of them might have included vegetation feedbacks, but my understanding is that a lot of these actually had fixed vegetation, and so didn't actually include that effect. When it comes to the,
sorry, go ahead.
I was just going to say, when it comes to the CMIP6 models, it's, you know, it's I don't know actually which of these did and which of these didn't include vegetation feedbacks. If you take, for example, the UK model, there are two different versions of the UK model in here. We had Gem 3, which doesn't include those feedbacks, and UK ESM, which I believe does include those. So it's variable between models once you get to the historical record.
Right. I guess my question is, so we know that there's so few terrestrial record, for example, for the mid-Pliocene, for temperature record, and there's certainly little record in places like Northern High Latitude or Antarctic. So if, depending on how the observation constraints derived, is this type of terrestrial temperature information also getting taken into account in this observational constraints of equilibrium climate sensitivity?
So in terms of the well, I think they are. I think the answer to that is yes, because when we assess climate sensitivity, one of the feedbacks that we included was the biophysical vegetation feedback. And in fact, the way that we assessed that was through paleo observations of vegetation change.
Mm-hmm.
So if I've understood your question correctly, my understanding is yes, we have made an attempt, let's say we have made an attempt to incorporate those feedbacks into our assessment of climate sensitivity.
Right, but paleo observations, do they also have terrestrial temperature change included? I guess that's my question.
Maybe we can pick this up in the discussion at the end. Yeah, so for the sake of time, we can wrap back around to this, and I saw there's a question in the chat from Jack, but we can talk about these further in the discussion. But we can go ahead and jump into Martin's talk. Again, 20 minutes, I'll try to give you a 2-minute warning, and then 5 minutes for questions on this, and then I think we can come back and circle back around to these questions at the end. So Martin will be talking on constraining climate sensitivity from paleoclimate temperatures, robust or weak approach. And you can go ahead and share your screen.
Can you see it now?
Yep.
Okay. No. Okay, so thank you so much for inviting me. So I'm going to talk about a very specific method now. I'm going to constrain climate sensitivity, which is the emergent constraint method using paleoclimate temperature. So all of this, Dan already talked about it, but basically there have been different ways of estimating climate sensitivity that arise particularly in the latest IPCC. And so one of the way was this like process understanding thing where you divide the global climate feedback into its individual component. This kind of approach, usually they're a bit more observation based or like based on physical theory. And I think there a bit like less trust in climate models, which is something that the emergent constraint approach is a bit more based on. And so a way of representing the emergent constraint theory is as simple as this kind of linear relationship, which is like climate sensitivity is equal to something. And here you're going to take into account model evidences and observation evidences. And so this is what I'm going to talk about right now. So the emergent constraint theory is the idea is that you can find a relationship between two variables of the climate system. Let's say climate sensitivity here, I put it as S, and the temperature of some past climate. And that relationship should exist in an ensemble of climate models that here I represented as blue dots, so that you can build like a real statistical relationship, which is going to be the red line here. And then the idea is that you're going to use this red relationship by putting a geological reconstruction of the temperature of those paleoclimates, so a temperature that exists in the real climate system, so you can infer the real value of climate sensitivity. And so, as I said before, you can just write it as simple as S is equal to some regression parameters times the paleoclimate temperatures. And so the way you do it is basically you only need an ensemble of climate models that are going to simulate the same past climates. And so thanks, we have the Paleoclimate Modeling Intercomparison Project, which designed those paleo simulation with similar boundary conditions across different generations of modeling. And so you can use this ensemble of models in emergent constraint framework. And so in the latest, so PMIP4, there have been like 4 big past climate that are simulated: the last interglacial, the mid-Holocene, the mid-Pliocene warm period, and the last glacial maximum. And when you try to apply emergent constraint and you want to use those paleoclimates, there are basically 4 main aspects that you really need to take into consideration. The first is that you always want the largest ensemble of models possible, because here emergent constraint is something that is based on statistics, so you really want to avoid like large intermodal differences and outlier effect. Of course, you want an observation that is really reliable, which is a problem in geological data. Usually, the further you go, the more uncertain you will be about your geological reconstruction. Ideally, you also want the largest signal-to-noise ratio, which means that you would like to avoid paleoclimate that are not so different from pre-industrial temperatures. And the last point is actually very interesting, but it's very specific. You actually need to know the value of climate sensitivity of the models you are using. And this is mostly a problem for models of PMIP1. So back then in PMIP1, before the Gregory method became something, the models simulating notably the last glacial maximum, they reported value of climate sensitivity, which are not necessarily clear. It's a bit unclear how they actually computed those values, and so it's difficult to compare PMIP1 models to the more recent models. And so if we follow those 4 points, basically we can exclude already the last interglacial and the mid-Holocene to constrain climate sensitivity, just because they have quite a low signal to noise ratio. The temperature are quite close of pre-industrial, so they're not ideal candidates, particularly compared to the Pliocene and the last glacial maximum, which are have much stronger temperature signals. So just to briefly summarize about the last glacial maximum and the Pliocene. So the last glacial maximum is, of course, this part of the last ice age where the extent of the ice sheet was maximum. So particularly you had a big ice sheet on North America and Europe. And in terms of geological data, because it's quite close to us, geologically speaking, we have quite an abundance of geological data. So on the right here is a temperature reconstruction that is quite recent. It's from 2022 by Anna et al., where you can see that all those like colorful dots are geologically reconstructed temperature data you can actually use. And then by using this kind of statistical filtering method, you can build those like global last glacial maximum temperature reconstructions. For the Pliocene, it's a bit more complicated because the Pliocene is quite different between what it was in PME3 and PME4. So in PME3, the Pliocene simulations were defined as an agglomeration of all the interglacial periods, all the interglacial peaks during the Pliocene, while during PME4, the Pliocene was really like a well-defined time interval. So here is all those like temperatures, like geologically reconstructed temperatures you could have during PME3, which is like you have a much lower amount of proxy data during PME4, and in particular there is quite a big scarcity of data at the pole because the time interval is much more restrained. And I didn't mention it, but so the Pliocene is a warm paleoclimate, which differ from the last glacial maximum. And so a way of seeing how good those paleoclimates are in emergent constraint framework is that you can build this kind of correlation map where you look at the model temperature and how it correlates with the model climate sensitivity. So here is an example of the model sea surface temperature at the last glacial maximum with the climate sensitivity of models during PME2 and PME3. And you can see that correlation does not look so good. There is basically limited significant negative correlation patterns in the tropic, which is what you expect. It means that the higher the climate sensitivity of the models are, the more cold they get. But there is also this like weird, very strong positive pattern in the Southern Ocean, which is unexpected and is going to bias your results. Fortunately, it gets better when you start to include the more recent models of PME4, and then the correlation gets like more extended into the subtropics. But I will show later that it's actually also biased because this result only comes from a single model, which acts as an outlier. For the case of the Pliocene, it's quite different because the correlation looks good on almost like global scale. And that was on the case whether you would isolate Pliomip1 or just isolate Pliomip2. So the Pliocene was always much better than the LGM, even before like PME3 and so on. And so then the idea is that once you have your ensemble of models, you just take you just compute the temperatures you want. You can focus on just tropical temperatures or global temperatures, and then you put them in this kind of scatter plot with climate sensitivity, and then you build your emergent relationship. And so this is what we did in 2020. So here you can see that the emergent constraint relationship of the LGM on the left and on the Pliocene on the right. So back then we used Bayesian statistics, and so that's why you have all these like multiple regression lines. So I'm not going to go into details into this method. What is important to look at here is that for the case of the LGM, the final estimate of climate sensitivity, which is this purple arrow you can see on the x-axis, is actually larger than the estimate you will get from Pliocene temperature, despite the fact that the observed back then in 2020 for the Pliocene was much more uncertain. And one of the reasons is you can see that again, the quality of the correlation at the LGM is just not good. Models are going like in every direction, and they don't seem to really agree between each other on what they're doing, despite agreeing quite well with what the reconstruction is telling us. So to summarize so far, I show you that we can effectively use paleoclimate temperature in Emergent constraint framework to constrain climate sensitivity. But if you look only at the constraint, it seems quite weak. If you have an estimate of climate sensitivity, the upper bound at least that easily exceed 5.5 Kelvin, even 6 Kelvin in the worst cases. And on the contrary, the Emergent constraint that come from Pliocene temperature seems very robust, and it's actually getting better and better as climate models are simulating the Pliocene. So now I'm going to talk about more in details about those two last points. And first, I will start about the LGM. So the fact that the relationship between LGM temperature and ECS is bad has not been the case like all the time. So back then in 2012, when Hargreaves et al. Looked only at the PMIP2 ensemble, and so the PMIP2 LGM temperature versus ECS, the correlation was actually much better, and it was just extended on almost all the tropic. But there was still this like weird positive pattern that would also exist in the Southern Ocean. But it is true that the correlation that arises from the PMIP2 ensemble itself looked actually better. Here I'm showing you the tropical sea surface temperature of the LGM versus the ECS of pools in three ensembles, so PMIP2 in green, PMIP3 in orange, and PMIP4 in blue. And you can see that the quality of the correlation when you look at only PMIP2 is much higher than the quality of the correlation in other ensemble. So one of the first hypotheses that came of this is that maybe it's just a generational issue, is that PMIP2 is so old that when modeling centers started to implement dynamical vegetation or some effects related to aerosols, then just the correlation collapsed because you're comparing models that are completely different. But as Dan said just before, it's actually not really the case because, first of all, there were not that many models that implemented dynamical vegetation in PMIP3. And then if you actually do statistics and if you look at if those ensembles are actually statistically different, they are not. Statistically, they are almost all the same. The median do not differ really. It's really difficult to say that this is the reason why the correlation looks so bad. And so instead, we looked at different issues regarding the climate of the last special maximum, and we try to categorize these issues into structural issues and state-dependent issues. So when we talk about structural issues, we talk about issues that arise from the simulation of the last special maximum itself, and mostly due to uncertainty in boundary conditions. And then when we talk about state-dependent issues, we talk about issues that arise from differences in climate dynamics that come from comparing warm climate and cold climate. And here the main problem is that climate sensitivity, as it is currently, is being mostly diagnosed from warm simulation. So typically you do 4 times 2 simulation. And then you try to compare that to the cold temperature of the LGM, where climate feedbacks probably behave in a different way, as it has been also shown now in the IPCC. So a very good example of structural uncertainties is the ice sheet forcing. Here is a map of variance in outgoing surface shortwave radiation, where you can see that the biggest source of variance at the LGM is coming from the Laurentid ice sheet, but also like regions of sea ice around the globe when you look at the entire PMIP ensemble. And it's not entirely new, actually. Already in 2017, there was a study that looked at how the contribution of ice sheet to last special maximum cooling could differ across different climate models that you can see here on the x-axis. And that contribution can change from 20% to up to 70%. And so considering the ice sheet forcing is roughly half of the total forcing of the LGM, we concluded here that it's most likely a major source of noise into the emergent constraint between LGM temperature and climate sensitivity. And in terms of state-dependent issue, we mostly talk about climate feedback, and here I'm showing you the example of cloud feedbacks. So we made several analyses where we double carbon dioxide from pre-industrial conditions on panel A, double carbon dioxide from LGM boundary condition panel B, and half carbon dioxide from pre-industrial conditions on panel C. And so, of course, it's a bit difficult to see, but there are differences in patterns on the global scale, but also tropical scale. And so when you actually calculate the value of the cloud feedback, you realize that when you halve carbon dioxide from pre-industrial conditions, you will end up with a global cloud feedback that is much lower than when you double carbon dioxide, whether from pre-industrial or LGM conditions. This is interesting because these results actually change drastically across climate models. This is something we got from MPI ESM 1.2, but you could see that in some other models, notably MIROC, actually the LGM boundary conditions impact much more the changes in cloud feedback than halving or doubling concentrations of CO2. This large model difference in state dependency on cloud feedback is also probably a big contributor to the weakness of the relationship between LGM temperature and ECS. Finally, another problem is at the time of the research, and I'm really emphasizing on this, at time of the research, there was only a single model that has a high climate sensitivity. So climate sensitivity above 5, which was CSM2. And it's a bit of a problem for the LGM, as I said at the beginning, because basically if you include CSM2, you will end up with a correlation map, which is on the top. But then as soon as you exclude CSM2, you will have the correlation map, which is at the bottom. So basically, CSM2 is responsible of the correlation between LGM temperature and ECS. And it's a bit of a problem to have such a strong outlier because it might be that the apparent high correlation is characteristic of CSM2 rather than actually showing the behavior of high climate sensitivity models. And so now to talk more briefly about the Pliocene, because this is quite ongoing and future work. So for the Pliocene, there are not that many issues, actually. As I said at the beginning, correlation map looks really good. And the biggest concern back then was the very large uncertainty we had on the geological reconstruction. But if you look at the correlation that exists between climate sensitivity and global or tropical sea surface temperature of the Pliocene, between PLIMIP1, which is here in red, or PLIMIP2 in blue, you can see that the quality of the correlation is really high, and it actually gets better in PLIMIP2.
2 minutes.
So one of the questions, of course, you can ask yourself is that, is it actually too good to be true? So on the right is a map of the geological data of the Pliocene we have that is currently used in PMIP4. And you can see, as I said at the beginning, there is quite a scarcity of data in the polar oceans, particularly in the Southern Ocean. So there might be that the estimate you can get from Pliocene temperature will be really heavily biased by the reconstructions you actually provide. Something good, though, that exists in Pliocene simulation is this abundance of sensitivity experiments. They have a lot of sensitivity experiments where they interchange the ice sheet of the Pliocene or the vegetation or CO2. And so we could learn how sensitive the relationship between Pliocene temperature and ECS is to those changes, something that will be ideal with the LGM to really pin down what is the contribution of ice sheet forcing. And finally, of course, you could combine this kind of very strong estimate with the historical emergent constraint to have an even better estimate. And to conclude and not just talk about the Pliocene, actually some research that is currently made on MyOMIP1, And so potentially there could be the inclusion of the myosin into emergent constraint in the future. So to summarize this talk, here I show that you can constrain climate sensitivity with paleoclimate temperature in this kind of efficient and really promising way, which is emergent constraints, and it gives results that are similar to other methods. So the last glacial maximum is widely simulated, but it seems to be quite a weak emergent constraint. Climate sensitivity models and sensitivity experiments could either improve that constraint or just give us information on why is it so bad. And so finally, the Pliocene is clearly the most robust constraint today, but there might be some large uncertainties that are neglected. Yes, thank you.
Great talk. Thanks, Martin. Are there a few questions specific to Martin's talk before we open it to a general discussion? Yeah, Dan.
Thanks, Martin. Really nice talk. I guess just to comment on the Pliocene. Really, you mentioned the uncertainties in the temperature reconstructions, meaning we're not quite sure where we should be on the y-axis, I guess, of your plot. But also the major uncertainty with using the Pliocene for emergent constraints is that there's quite a large uncertainty in the CO2 that we should have put in the model. So we put 400 ppm into the models, but if the actual CO2 is 350 ppm, which is still consistent with the Paleo data, then basically it means that we are it would basically bias your estimate of what your best estimate of ECS. If CO2 was actually 350, then climate sensitivity would be higher than what you estimate from this emergent constraint, just because we did the wrong experiment with the GCMs, basically. So just a comment, really, that's another uncertainty that has to be taken into account.
Yeah, I can add actually that today the reconstruction is much better, and today we know that it's actually positive. This was still in 2020. So what I was trying to show on this plot, it's just the legend. It's not ideal, but it's exactly what you're talking about here. It's like different it's the same model doing the Pliocene, but at different CO2 values. And so there are a bunch of this like Pliocene models that are doing this like 560 ppm or like 400 or 350 ppm and so on. So that is clearly something we could have a look at. Yeah.
Great. One more quick question for Martin, or maybe we can even kind of go ahead and open things up a bit. Oh, Mike.
Recently, Ramanathan and some colleagues had a paper that came out that really looked at equivalent potential temperature, I think it was, so including the effect of water vapor in that. Would it be more stable if one really were looking at that, because it really considers more the amount of energy that's involved than just temperature, which can be affected by various factors, and so getting the humidity in there, the absolute humidity and the energy in that, might give a more stable kind of estimate of what's happening over these ranges. So
you mean instead of plotting?
Well, instead of just using temperature, as you get, we have much greater temperature response in high latitudes than low latitudes. Partly has to do with what's happening with respect to the water vapor. If you look at equivalent potential temperature, which I think is what he was looking at, you sort of see a more even energetic change over the Earth. So I guess I'm just wondering if that's a better thing to use than particular temperature, just temperature, which is sort of one measure of the amount of energy involved.
But then I'm not sure if your water vapor or humidity reconstruction is more reliable than the temperature one in like past climates. I would trust more a temperature reconstruction. I'm not even sure they are proxies for humidity.
Yeah, I was just going to say, we have quantitative temperature reconstructions, but humidity is a kind of a wild card with our current available approaches.
Yeah. Well, the models provide at least some indication of that, though, about.
Absolutely, yeah.
So.
Was that your question, Tripty? Or
Yeah.
Okay.
Oh, sorry. So I guess, it's always tight with time. So let's kind of open it up a bit more to more general questions. And I don't know if we want to loop back around to the terrestrial and vegetation responses, or there's other things people want to discuss. No, we only have about 5 minutes left. I see Jack's comment here. So I think this is back to climate sensitivity. So I don't know if Dan, you can see that it says, thanks for the detailed response. Related then, I'm a bit at odds with the only ascribing high confidence to climate sensitivities being greater than 1.5 with the Grand Central estimate between 4 independent approaches of about 3 degrees. So he says, I don't think I would conclude that Earth system or equilibrium climate sensitivity of Earth right now could be even as low as 1.5. I think most people would agree with that, but I don't know if you have a comment on that comment.
Well, I guess we did. I guess we did say it was very. I'm just trying to remember the final assessment. We did say that it was likely greater than 2.5. I think the numbers that Jack's talking about are the overall. I think maybe I wasn't clear in my talk about when I was saying what parts of the assessment were just coming from the Paleo and which were the overall assessment. So the Paleo on its own, that's where the assessment, it was very likely that ECS is greater than 1.5 came from. Whereas when you combine the different lines of evidence, then you get the very likely greater than 2.
All right, John, I saw your hand up. Question.
Yeah, so I have a question for Martin. I think it's really surprising to say that the LGM provides a weak constraint on the climate sensitivity. So my question is, do you have any suggestion about how to make the LGM a stronger constraint? And a related question, so perhaps if emergent constraint, this method for LGM provides a weak constraint, do we want to explore the other methods instead? Thank you.
Yeah, I think it might be a method problem. I think it's always tricky when I say it's a bad constraint, because then the other methods and people using other methods are not happy. I think it's bad in the emergent constraint framework, but if you use this kind of methods where you try to estimate the individual forcing, so the forcing coming from the ice sheet and so on, it actually looks good, the LGM, because you have so many evidences. But then you might have some issues, for example, because usually this kind of method, they will simplify ice sheet forcing as just some kind of albedo, and they don't actually consider what is the impact of ice sheet on like LGM global circulation, which is why you would like to use emergent constraint. For me, the way of making it better will have just to have more, I don't know, sensitivity experiments and try to really understand why, like can we actually make it better with the ice sheet forcing, and how strong it is, and like what is the actual quantification of noise on the relationship. Because that's a bit the problem of the study we've been doing, notably, is you can of course pin down all these problems, but it's very difficult to quantify like the actual bias on your relationship.
Thank you.
maybe just quickly, so one thing that would improve things would be to have more models that have extreme climate sensitivities run this. Yeah, like you did.
Can I just respond to Mike? Mike had a question in the chat, actually, which was quite an interesting one. He said, have similar studies been done to estimate the equilibrium sea level sensitivity? Well, I haven't actually heard it being called that before, but people have done that effectively from the paleo record. So, for example, there's a couple of I think there's Elko Rowling and Gavin Foster and Ed Gasson had one as well, where they looked at various different paleo records and either did plots of equilibrium sea level against CO2 or equilibrium sea level against global mean temperature change. And basically they see some, well, initially with the data that they had, there was some indication that there was a sort of a sigmoid shape to it, and that you had under relatively low CO2 changes or relatively low temperature changes, you got one gradient, and then you get an increase in the gradient as you start to melt East Antarctica somewhat, and then it flattens out a little bit again. So yeah, people have looked at that. I don't think they called it sea level sensitivity, but that's effectively what it is.
Great, thanks. So we're coming up on time, so I think maybe this will be the last question or comment by Ran. I'm happy to stick around longer, but I know people have other obligations, so let's maybe end it with this one. So Ran, you have a question?
Oh yeah, this is perhaps a quick comment to the data availability for Martin. So the data I think you're looking at was the Aaron McLemont. So that was really focusing on the mid-Pliocene interglacial. But I was wondering for what you're doing, perhaps a wider time constraint like 3.0 to 3.3 May would be good enough. And for that, you probably could get a lot more records. The other quick question I had is, so terrestrial temperature is not included in any of those analyses. So I was wondering what's the reason for that?
The main reason is because, at least for the case of the Pliocene, you have way more marine-based proxy data than land-based proxy data. It's much easier to reconstruct sea surface temperature because you have like foraminifera and I don't know, trillions of proxy data in the ocean. And basically on land, you have pollen, which are relatively, I don't even know if they're relatively good at the LGM. For the Pliocene, I don't even want to think about it. So that's why we focus on sea surface temperature.
Right, but there's some good high northern highlight shoot terrestrial temperature record, which might actually be directly relevant to the vegetation feedback. And yeah, might be something interesting to consider as well.
For the Pliocene, you mean?
Yeah, for the Pliocene.
I think it partly depends how much you worry about the dating and the time window. So when we look for Pliocene data sort of for the narrow mid-Piacenzian interval that they use in the modeling, I think we chatted to Ulrich Salzman and he found about 4 data points, but it is a very, very narrow window. If you allow that to expand a little bit, then you get a lot more data, but then you start running into difficulties about, is this sort of a glacial vegetation, actually, not deep glacial, but a relatively cold period of the mid-Pliocene, or is it an interglacial? And suddenly you do a very different GCM experiment if you were trying to best simulate that time period. So I think partly the reason that the records are dominated by marine is that in general, I know there are some terrestrial sites that are very well dated, but in general, the marine sites tend to allow you to focus more on the time window that the modeling is focusing on.
Right. Tamara Fletcher, I think she's currently working with Alan. She knows a lot of the Canadian Arctic Northern Highlight shoot record. And I think the other groups, Julie Bergen-Geddes group, they have Lake E record, which is very well dated. So, and it has very clear vegetation, glacial interglacial changes and signal. So yeah, so there's something to be considered.
All right, great. I'm happy to stick around and continue discussion. I know some people probably got to go. So at this point, I'd like to thank our speakers for a great talk and discussion. And thank you all for attending. Again, we'll be trying to continue these seminars fairly frequently, even over the summer. So I think our next one is planned for July. So stay tuned for that one. And again, if people want to stick around and discuss a bit more, I'm happy to do so. Thanks, everybody.